Okay, so deconstructing this question here. So there's a couple of questions inside the question, right? So have you learned how to read the stuff in the book? So this entire thing down here is called a grammar, right? And this grammar is made up of 3 productions. I specifically asked about the lambda expression production. Okay, which of those productions is the lambda expression production? Second one, this guy right here. All right, so my question is, what is the limitation of this dude? Well, first of all, what does that guy represent for us? We're starting to get into language stuff. What does the lambda expression mean to us? Yeah, it's a function. Okay, it's an unnamed function until we put it in an environment, but it's a function. All right, so if this is our definition of a function, what limitation does this function have? Well, what's a function? Tell me, just in general terms, what's your definition of functions? We've learned about this in a lot of other classes. A reusable chunk of code that you write once and called over and over and over again, right? Now, do functions have like a number of parameters that we can give them? What's the minimum number of parameters that a function might take? 0. What's the maximum number of parameters that a function might take? Who knows? There probably is some sort of real maximum. Maybe it's the size of an integer or something like that. I don't know if that's ever actually come up. But maybe it's 32,768 parameters, or it's 2 billion parameters. I don't know what it is, but the hope is we're not really hitting that limitation very often. So what limitation does this definition of the lambda expression give us? Exactly 1. We can't have a no parameter function. We can't have a 2 parameter function. We have a function that can only take in exactly 1 parameter. Now, if we're writing functions, isn't that going to be fairly limiting? So maybe in the world of 0 or 1 parameter functions, we can operate, right? We can always just say, you got to toss me a parameter. Look, I don't need anything, but you got to toss me something. Give me a 5, okay? I'm not going to use it, but I can work with that just for a legal call. But if you need more than 1 parameter, things are going to get dicey unless you hide those parameters inside of like a list or something like that, right? Like give me 1 parameter, but the parameter is actually a variable environment or something like that, a dictionary. All right, so limitation would be that our lambda expression only supports exactly 1 parameter, 1 input. All right, questions on that one? Okay, homework assignment was to create some constructors and observers, right? I'll leave our environment up there. I'm going to get rid of the stack stuff. Call that good. And I'll get rid of, whatever, we'll leave that there. Okay, so let's go into the book here. So we decided we were going to have a constructor for a var expression, a lambda expression, and an app expression. And then we were going to have an observer for the operator and operand of an app expression. Is that the assignment? Sound accurate?
I thought we were just writing the predicates and then doing the observer for the operator.
So writing a predicate for whether or not this is the, whether something is a var expression, whether something is a lambda expression, whether something is an app expression. All right, fair enough. Well, I think I only wanted 5 things, but whatever you wrote's fine. As long as it's one of those 2. If you wrote constructors or predicates, it's kind of actually the predicate would probably be the harder thing to write, but not by much. But I definitely asked for observers for the operator and operand of the app expression, right? Does anybody know what I actually officially asked for the first 3? Was it predicates or was it constructors? It was the predicates? Okay. All right, so let's go ahead and write the predicate. So we're going to take in something that is an Elsi expression, And we want to know, is it a var expression? So if it's a var expression, that means it's only an identifier. So this would be define var exp lambda Elsi expression. And this guy will return symbol Elsi expression. Like that. Look reasonable? That's just an identifier. Return true if the lambda calculus expression is an identifier. Return false otherwise if it's anything else. All right. Next one is something a lambda expression. Define lambda expression to be a lambda that takes in an Elsi expression. All right, now what is a lambda expression? A lambda expression is a list whose car is a lambda, whose catter is a list containing exactly one element, and whose CADDR is a lambda calculus expression. That makes sense? Okay, so before we write this, well, I guess let's write this first and then we're going to write a higher level one. So we need to find out, is it a list? Is it a list whose car is a lambda? Start with just those pieces. All right, so we're going to return list Elsi expression. That's one thing, right? And CADR, well, actually, and list CADR Elsi expression. And what else? If we keep breaking this down, what other things must be true for us to determine whether something matches this predicate? Well, we already, car has to be equal to lambda. I guess that's true. Since it's a list, we can ask that at this point, right? So we can say and EQV car Elsi expression is a lambda. Hold on, I didn't close one of my... Oh, actually, a single and will take in a list of things, I believe. I think I can and all these things together in a single and. So and this. So here's the first part of my and, second part of my and, third part of my and. The car of the thing is a lambda. What else do I need to know? Oh, X. Yeah, I gotcha. Going back to this, do I need to know that right now I'm checking, is this guy a list? Specifically, is he a list that only contains one element? Right? How do I ask, is it a list that contains only one element? Well, which predicate? Well, null would not return. I want to know if that's a list that contains exactly one element. Check if the length's equal to 1. So, and I'm going to start kicking these down. The length, well, equal length CADR Elsi expression is 1. And if its length is 1, I want to know if the one thing that's in there is a symbol. Correct?
Yes.
Let me ask you this question, just as a pause. Why does it say identifier here instead of another lambda calculus expression, which could be an identifier? Could also be a lambda calculus expression that's not an identifier. This guy specifically requires a name of a variable. Right? That's how it works in Java and all these other languages. Right? Okay, so yes, this is an example of a lambda calculus expression, but it has to be a very specific example. So rather than saying it's a lambda calculus expression, they've just put in exactly what it is. So if I know this guy is a list, and I know it contains an exact length of 1, then I also want to ask, is the one element that's in there a symbol? So and symbol CAADR lambda calculus expression, the car of the cooter. Make sense? What else? The car of the cooter must be a what? What's that guy? A lambda calculus expression. So I actually need a predicate for determining whether something is a lambda calculus expression. And what's a lambda calculus expression? Isn't a lambda calculus expression either one of these, or one of these, or one of these? Okay, so the final and is the car of the cooter. So we're just going to actually, we're going to say the car of the cooter of the lambda calculus expression is, presuming that we write a predicate called lambda calculus expression. It's one of those. So that's our lambda expression. Okay, what about our app expression? Takes a lambda calculus expression, and what do we do with it? What is an app expression? It's a list containing exactly 2 elements, right? So and list Elsi expression and equal length Elsi expression 2 and Elsi expression car Elsi expression and Elsi expression CADR Elsi expression. It's a list, specifically it's a 2 list, whose car is an Elsi expression and whose catter is an Elsi expression. All right, then what's our predicate for Elsi expression? This guy's a lambda. That's going to take in some expression, and we want to know whether it's an Elsi expression. How do I know something is an Elsi expression? Yeah, if it's any of those, right? If it's a, what did I call the first one? A var expression, a lambda expression, or an app expression. So, or var expression, expr, lambda expression, expr, app expression, EXPR. If any of those guys are true, then this guy must be a lambda calculus expression. Oh, I called it EXP. That's EXP. That's that. All right, that makes sense? All right, what about our observers? So we wanted an observer for define, what do we call it? We can call it a get operator. And this guy will be a lambda that takes in a expression. And if we want to go ahead and use, you didn't have to do this part, but if you want to use our guys, we'll say if app expression EXPR, if that guy's true, then go ahead and return the car of our expression. Otherwise, maybe boil down to false, something like that. There is no operator. Define get operand. Lambda takes in an expression. We ask the question if app expression EXPR, then return the catter of our expression, otherwise return false. Does that make sense? Now, my guess is that most of you did not write, certainly your lambda expression, that verbosely, right? Most of you operated off the premise that we've been operating off of, which is fair enough. It says, look, what you're throwing me is a legitimate lambda calculus expression. Therefore, we have three productions. We have one production where the thing isn't even a list. It's a symbol. That's our var expression. This guy's pretty straightforward. That should have looked, everybody should have looked pretty much like that, right? Okay. The other one, well, the other two are both lists. Okay. One of them is a list whose car. So we can ask if it's a list and the car of that list is equal to lambda. You might have written it with just those two questions, right? Am I looking at a list, and does that list have a car that's a lambda? And that would have been sufficient. Making that assumption. You know, the reason we kind of went through this like this is really kind of, we want to practice piecing apart these things because we're starting to work on parsers. All right, so if you didn't go into this level of detail in your homework, that's okay. It's fair enough. We've set the precedent already that you can assume the person's passing you a legitimate lambda calculus expression. All right, so this guy verbosely checks bone structure as to whether what you gave me meets all of the requirements of a lambda calculus expression, specifically the lambda production of it. That make sense? Okay, and that's going to be very important when you're actually talking about interpreters or you're talking about compilers, especially when we start dealing with languages that have specific limitations like we discussed earlier today. Well, we discussed it last class. I think I actually mentioned that near the end of last class, the single parameter limitation. Pretty positive. Anybody corroborate that? I mentioned it last class, didn't I? I'm almost positive I did. So listen to the video if you want the quiz answer. Um, so in any case, we look at this and we see that this is a very, very specific implementation. Therefore, in order to determine whether this is a legal lambda, the lambda expression production of this guy, we need to be explicit. Does it start with a lambda? Does it then have a list? Does that list have exactly one thing in it? And is that one thing a symbol? It's an identifier. What would I do with that identifier if I'm taking it the step further and I'm an interpreter? What would I do with that identifier? If I were processing this, if I was the book uses the phrase apply. If I'm applying this lambda calculus expression, what would it do with that identifier? Is it just there for show? When we write functions, what happens at runtime to our parameters? It's after 1 p.m. We're all awake up by now, right? Yeah. Okay, I believe Hinkle when he says he's not awake. Okay, but he's the only one. That's how little I think of you. That's fair. That's fair. That's fair. If I have a function in Java and I pass in a parameter a, what happens at runtime to a? Cat, dog, or it turns into its value. Okay, it turns into its value. The variable is resolved to its underlying value, right? Okay, so we're going to have to resolve that guy when we apply this production of the lambda calculus expression. And when we resolve it, we're then going to extend our environment, right? If I have a function, here's a function. This function is creating a new environment, correct? With one additional variable binding. Whatever the value that was passed in here associated with this symbol. And this lambda calculus expression will be applied, using the book's lingo, okay, will be applied in that new extended environment. The environment that now has this additional variable. So other variables that might still be within the scope are accessible, right? If we had a Java program, we had some global variables up here, and I had a function down here, I have access to those global variables from within that function, right? But I also have access to some new variables that were born in this brand new scope that came into that function. The scope that was extended right here. So then I'm going to apply this lambda calculus expression in terms of this new extended environment. That makes sense? And this is where we start getting into some of these phrases like all variables resolve to their most local definition. Let's say this variable was named A. Is it possible that we have more than one A in all of our scopes? But the only one that's important to us right now is the most local definition of A, because that one is said to shadow the more global definitions, right? When I go to resolve variables, I'm going to check locally first, do I have an A around here? If I don't, I'm going to bounce up one scope. Check there, okay? So if I have an A up here, but I have a more local A, well, we're going to roll with the more local A, and we're going to stop searching. Does that make sense? Okay, so hopefully we're starting to see how these different pieces that we're working with are starting to kind of connect with each other loosely, right? You know, we see how they all kind of play a role in where we're going with this. Okay, so any questions on the homework? Now, what if we were building constructors for a var expression? Let's start off with that one. So if I'm going to build a constructor for a var expression, what's this guy going to take as a parameter? Symbol? And it's just going to return that symbol. That's my constructor for it. If we went with more of an A-list definition of this guy, maybe we would return the list containing var expression followed by the symbol. something like that. That's not the direction we're going right now, but we might do that. What would be the advantage of, instead of saying the symbol like that, us returning the list containing var exp and the symbol? What would be the advantage of that definition? Later on. So before, I've referenced something called a type inference engine, right? Even in previous classes. When I say type inference engine, what pops into mind? What topic were we discussing when we mentioned that? You guys are just ticking me off today. Cat, dog, or loosely typed languages? Okay, Hinkle's got 2 in a row, right? Okay. Loosely typed languages. So we've talked about loosely typed languages as being lower performance languages, right? Okay. So why are they lower performance? Why are they slower? So they have this dude called a type inference engine. We don't necessarily know what kind of value our variables hold, because we haven't put a little sticker on the outside of it or written on it with a Sharpie saying this guy holds a number or this guy holds a string. He's a box that holds something. And we got to peek inside the box to find out what's in there. That makes sense? So if we have something like this, is that what we might expect in a strongly typed language? Where we've predefined the kind of thing that we might find in the box? Or could there be somewhere kind of like halfway in between, where maybe we take our program, so let's take a loosely typed language like Python. We read in all those symbols, and we convert them into another format. All right, we convert it into the format like kind of prepared for execution. I mean that in like that creepy, like death row type of. So Python itself, when we write that code, Python's just the example we're using for a loosely typed language. Pick your favorite loosely typed language, PHP or Ruby, whatever. When we write that, it's still going to have kind of a human-esque type of syntax to it, right? Would it make sense that when we go to run it, we type in Python and the name of our program.py, that something occurs before it just runs it? Is it probably going to kind of go through that stuff and kind of organize it in some interesting way that's going to allow it to maybe more conveniently execute the program? All right, so no matter what we wrote that language to look like, there is some preparation that's going to be involved. Okay? In a compiled type language, that preparation is pretty severe, right? There's, we're basically parsing it into a sublanguage. What does Microsoft call that for the .NET languages? Pop quiz, trivia. When Microsoft takes a C# program and it initially parses it, we'll just start using the word parse because that's where we're going with this. It initially parses it. What does it turn that into? Missile, Microsoft Intermediate Language. Okay, daily double. Is that high five? Where's that quote from? Yeah. Hey, Cole, you're on top of things today. So what happened? I blacked out. Where's that quote from? Wasn't it? Was it Billy Madison? When all the people came together? No, it wasn't. It was from something newer than that. Because it was Will Ferrell who had the quote.
Then it was probably old school.
It might have been old school. Probably it was old school. Yeah, you're right. Man, I asked the question, didn't even know the answer. Thought I knew the answer, and then Hinkle had the answer. Wow, sign of the apocalypse right there. All right. So, Microsoft, their compilers turned it into Microsoft Intermediate Language, kind of a staging language that can then be taken and at runtime turned into that low-level language that compilers do, right? Because ultimately, low-level languages are going to put the thing into the format that the CPU can kind of digest. So we're having to take lots of steps there because at that point, we're not necessarily thinking about convenience. Okay. At that point, what are we doing? We're effectively setting the table for our CPU so it can work through the buffet the quickest. Does that make sense? See, I just had lunch too, and I have all these food references. All right. So in any case, when we read in our Python code, our loosely typed language code, we're going to do some preparation to get it into a format that we can work with. So it wouldn't be unreasonable for us to want to go ahead and throw things like var expression in front of things, stuff like that. Because if we could identify it early as being one of those guys, it might help us later on when we actually go to process it, because maybe we wouldn't need something this scary to find out if something was a lambda expression. We can just look at the car of it and say, what are you? If it says lambda expression there, I can trust that the rest of it is one of those because we've pre-processed it. That make sense? So kind of keep that in mind with the direction we're going to be working with these things. But for right now, I'm going to leave this guy as just an S. Now, if I build the constructor for a lambda expression, what are the parts of a lambda expression? Go ahead.
The identifier and the Elsi expression.
See, now he's like rolling with it. So I'm just going to keep answering. Yeah, we have two pieces, right? Two different things that we need in order to accurately build a lambda calculus or a lambda expression. Okay, so we're going to have a lambda that's going to take in an identifier. We'll call that a simple S. And it's also going to take in a lambda calculus expression. And what are we going to do? We're going to build a list out of the word lambda, a list out of our S, and our lambda calculus expression. So this is our parameter list right here. This is the body of the expression, and it starts off with the word lambda. Define constructor for app expression. What are the pieces to the puzzle for an app expression? Okay. Or the direction the book's going to go with this is it's going to call it the operator and the operand. Okay. And we've kind of already seen that when we looked at our observers. So, but he's right. Lambda calculus expression 1 is going to be our operator. Lambda calculus expression 2 is going to be our operand. And what are we going to do with those guys? We're going to throw them in a list. List, rater, rand. Like that. That make sense? All right. All right, so these observers, we've written those two, correct? We wrote an observer for taking an app expression and producing the operator. We've written an observer for taking an app expression and creating the operand. What about an observer for the lambda expression creating a body? Get lambda body. You know, they're kind of using a naming convention with these arrows. So lambda expression to body is the way they're writing these. So if I want to adopt that, we'll say lambda expression to body. That's going to be a lambda that takes an Elsi expression. And how do I get the body of an Elsi expression? here's our lambda expression. How do I get the, well, which piece of that is the body? This guy, that's the body of it, right? How do I extract that one piece? CADDR? Yep. So this guy's going to return the CADDR of our lambda calculus expression. It might have been a wise idea to first ask, is it a lambda expression, one of those guys? But, you know, we didn't. But we certainly have the tool for it. We wrote it, right? Similarly, we have a lambda expression to bound var. This guy is going to be a lambda. Take an Elsi expression. And what's the bound var in a lambda calculus expression? That's the identifier. How do we extract that identifier? CADR, the car of the cooter. Yep, so the cooter, well, hold on. It's the car of the cooter, right? Because that's actually a list. The car of the cooter will give me this piece. The car of the cooter will give me the identifier that lives inside that list. Make sense? All right, so CAADR LC expression. So that's that observer. We'll write that one real quick just for completeness. Define that guy to be a lambda that takes an LC expression and returns an LC expression. Make sense? Okay. So now they've introduced this function called occurs free. And this guy's going to return a true. We know it's a predicate because a little question mark thing there. And what it's going to do is it's going to take in an expression. And it wants to know whether the variable we're looking for in there occurs free in that expression. Now, there's a couple of things here. What does it mean for a variable to occur free in an expression? Well, first we have to ask the initial question is, what does it mean for a variable to occur? What does it mean for an identifier to occur in an expression? If we go back to our definition of lambda calculus here, up here. A variable occurring indicates places where we've used a variable name in a way that was not defining the variable name. That's what occurring means. So where are legal places for a variable to occur in a lambda calculus expression? Is this the variable? Is this a variable occurring? I tricked you. It's not. Why? Because that's where it's being defined. That's defining a variable right there. So a variable cannot occur there. It can occur here. This is us using that variable. It can occur somewhere in here. It can occur in here. It can occur in here. So the one place it cannot occur, because it's being defined in this place, it's being bound in this place, is right here. Does that make sense? Yes. Okay, so for your homework, I want you to write a function called occurs that returns true if a variable that we're searching for occurs anywhere inside of a lambda calculus expression, and false otherwise. Occurs, not bound. Okay, I want to know whether it occurs. That means, does it show up in here, 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 or here? Not here. That's where variables get bound in our current definition of lambda calculus expressions. So write occurs with a question mark that returns true if a variable we're searching for does occur in there. You know, actually, I think a better thing would be why don't we call it all occurs? Return a list of all variables that occur in a lambda calculus expression rather than searching for an individual one. So you can give you the scariest lambda calculus expression you can see where you have lambdas inside of lambdas inside of lambdas inside of lambdas. Ultimately return a list that this is no more difficult. This actually maybe makes life a little bit easier because then you don't have to test it with a search term. Return a list that contains all the individual variables that occurred inside that lambda calculus expression. Make sense? All right, I will see everybody on Friday.